This problem where it's asking us to find intercepts and asymptotes. So we're going to find that information first, kind of using what we know from pre-calculus. So first of all, if we want to do the x-intercept, that means we want to put in a 0 for y. So we have 0 equals 5 over x squared minus 1, and we can write this as 0 over 1. Now, if we cross multiply, we're going to get this way, we get 5 equals 0 going this way. And that's a false statement, which means no x-intercept. So that means I'll put that underneath here. Okay, so I'll put that no x-intercepts. Okay, so there's none there. Okay, so we'll put that down in a second. Let's also look at asymptotes. So if you want to find the VA, this is the vertical asymptote. What we do is we're going to set the bottom always equal to 0. And this is only for rational functions where we have this. So x squared minus 1 equals 0. We have x squared equals 1, and x is equal to plus or minus 1. So we have vertical asymptotes at plus or minus 1. We'll put those down the bottom later. Okay. We also want to do HA. HA is the horizontal asymptote. Now, in this case, the highest power on top is less than the highest power on the bottom. That means that the bottom is going to be increasing a lot faster than, well, the top doesn't change at all. It's just going to be 5. So as this gets bigger and bigger and bigger, the whole result's going to get smaller, which means it's going to end up going to 0. Now, we did that kind of using pre-calculus, but you could also take the limit as x approaches infinity. If we did that, we would divide everything top and bottom by the highest power in the denominator. So we would do 5 over x squared over x squared, and minus 1 over x squared. And then we'd apply properties of limits there. We would end up getting a 0 also. So we actually have some pieces of information already about the graph. So first of all, x-intercepts is none. The VA is where we set the bottom equal to 0. We got x is equal to 1, and we got x is equal to negative 1 on that. The horizontal asymptote was y equals 0. Now, what that's going to look like on our graph is we're going to put these as dotted lines. So I'm going to put some dotted lines here, and then I'm going to put dotted lines on that one. And here's a horizontal going through. Make that straight. Horizontal line is going through like that. So that's going to be this kind of setup that we have so far. We don't have any x-intercepts on that. And so this is what we have so far. Okay, so now we have that complete. That's kind of pre-calculus work. Let's jump into now actually finding the critical numbers. So critical numbers, we need the first derivative. Now, the way this one is written here, we could go ahead and use the quotient rule for that one, and that would work out fine. What I'm going to do is I'm actually going to rewrite this as 5x squared minus 1 to the negative 1 power. This was originally on the bottom, so we make it a negative exponent. And then we can actually just do this completely using the chain rule. Then we don't have to use the quotient rule for that. So y primed, we're going to bring down the power. So we're going to do minus 5. So negative 1 times 5. We do the derivative of the outside first. Okay, so we get negative 5. We have all that to negative 2. That's the derivative of the outside using power rule. But then we have to multiply it by the derivative of the inside. The derivative of the inside would be 2x. Derivative of the outside times derivative of the inside. Let's rewrite it with positive exponents. That's going to be negative 10x on top over x squared minus 1 squared. And that would be the first derivative. Okay. Now, when we talk about critical numbers, we want to see what makes the first derivative undefined. And of course, that's going to be 1 and negative 1. However, 1 and negative 1, we already know are vertical asymptotes. They also make the original problem undefined. So I cannot put negative 1 and 1 as critical numbers. Okay, so I can't find any critical numbers that way. The second way we find critical numbers is where we set the first derivative equal to 0. So that's what we're going to do next here. We're going to do 0 equals negative 10x over x squared minus 1 squared. We'll write this as 0 over 1. Now we're going to cross multiply. So if we cross multiply that, we're going to get negative 10x equals 0. Multiplying, cross multiplying there, and we get x is equal to 0. So the only critical number that we have here is actually going to be just 0. That's all we have there. Now, when we make our number line, we're doing our first derivative number line. I'm not only going to put 0 on there, but I have to also put the numbers that I have for my vertical asymptotes, because that's where I get division by 0 happening. So I can't include those in my answers. So that's why I got to put these on here to break it up into different regions. Okay, so we're going to do test numbers, -2. We're going to use -0.5, +0.5, and 2. We're putting these into the first derivative. Now the bottom is squared, which means that's always going to be positive no matter what. So we can pretty much ignore the bottom here because we know that's always going to be positive, regardless of what number we have inside here. So I'm just going to worry about the top. So -2 times -10 is positive. -0.5 times -10, that's also positive. -10 times 0.5, negative. 2 times -10, negative. Okay, so we get plus, plus, minus, minus for our sign configuration there. That's going to tell us for increasing negative infinity to -1, -1 to 0. We are not allowed to include -1 because it's not defined in the original function. So that's why we can't go negative infinity to 0. We definitely have to split this up this time with -1. Okay, so decreasing, we have to do the same thing. We also have to exclude the 1 there. So we're going to go 0 to 1, and then from 1 to infinity. Okay, so that's going to be where it's going to be. So increasing, we have these here, and then increasing, we have this here. Okay. Should I did those? I should have did those in yeah, so that's all correct here. Okay, so we have positive, positive, negative, negative, and that would describe that particular region. Okay, so now next thing we want to do is to find the relative max. Now, relative max we can do here because we've got a positive going up, and then we have a negative here. So it's increasing and then decreasing. We have a plus going to minus. That means that our relative max occurs at 0. Now, if we plug a 0 into the original function, okay, so relative max again always is using the original function there. So if you put 0 in there, we have 5 divided by -1, so we get -5. So the relative max here is going to be 0, -5. Now, relative min, we actually have to put D and E here, okay, because that does not exist. We don't have a minus going to a plus. So because of that, it's D and E for relative min. Okay, so next thing is we're going, and actually this 0, -5, let's go ahead and plot this now. That actually is going to be a y-intercept. So we get another point on our graph here. So that's going to be right there, 0, -5. Okay. Next, let's find the Hilbert numbers. In order to do that, we need the second derivative. Now, here's the first derivative. This is going to require us to have to use a quotient rule this time. All right, now we could actually bring this up and make it a product rule if we wanted to by do x squared minus 1 to -2, but I'm just going to leave it in this form here. All right, so let's write this out. We have first on the bottom x squared minus 1 squared, and this is going to be squared. We have the bottom x squared minus 1 squared. That's our g. We want to do the derivative of the top. f prime, that's negative 10, minus the top, negative 10x. When we do the bottom, that's going to require a chain rule again. Derivative of the outside, 2 comes down, x squared minus 1 to the first power, and then times the derivative of the inside, which is going to be a 2x. We want to do some simplifying here, certainly. That way we can, eventually we have to try and set this equal to 0. On the bottom, x squared minus 1, that's going to be to the fourth power. On top here, we have negative 10, x squared minus 1 squared. And then this, 2 times 2 is 4, times 10 is 40. That's going to be plus, negative, 40x squared. That's 2 x's. And then times x squared minus 1. We want to keep on going with this. We want to factor this one. We're going to factor out a common factor here of, we have negative 10 is a common factor. Negative 10 is a common factor. Or actually, let's just use 10. We'll just use positive. 10 is a common factor, as well as x squared minus 1 to the first power. Now, if we factor that out, we're going to take this first one divided by this. We're just going to get a negative x squared minus 1, that first part there. This part, we still have 40 divided by 10 is 4. And then we have x squared left over. This one's going to go away because it canceled out. X squared minus 1 to the fourth power. Next, we're going to cancel out this one, and that's going to become a 3. So I have 10. Okay, then let's combine this. We have negative x squared plus 1 plus 4x squared. Be careful with the signs on that. This is x squared minus 1 cubed. Okay, continuing with this. Y double primed is equal to 10, and then inside here we have 3x squared plus 1. We find Hilbert numbers. Hilbert numbers are when the second derivative is undefined. But again, it's only going to be undefined at 1 and negative 1, which we already know are not defined in the original function, so we'll ignore that. Next thing is, we want to set the second derivative equal to 0. Let's do that here. 0 equals 10 times 3x squared plus 1 all over x squared minus 1 cubed. And if we do cross multiplying on that, we're going to get a, so 10 times 3x squared plus 1. That's going to equal 0 when we multiply the other way. Now, I can't set 10 equal to 0, so I'm just going to set the 3x squared plus 1 equal to 0. Now, if we do that, we're actually going to end up getting a negative number for that. If we do 3x squared plus 1 equals 0, then what happens is, if we subtract the 1 and divide by 3, we get x squared equals negative 1/3. Now, we can't take the square root of a negative number, and we don't have any imaginary numbers that we're using here for Hilbert numbers, and critical numbers can't be imaginary. So because of that, we can't find any critical numbers or any Hilbert numbers that way either. So in this case, we actually have, for Hilbert numbers, we actually have to put here D and E. Okay, so there's no Hilbert numbers there on that one, because there was, so first of all, the numbers 1 and negative 1 make the second derivative undefined. However, they're not defined in the original function, so no Hilbert numbers that way. And then also, we tried to set it equal to 0, and that gave us imaginary numbers also. And so for that, that means that we actually do not have any Hilbert numbers at all. So when we do our number line on this, we still have to remember, okay, so let's label it y double primed. Okay, negative 1 and 1. Okay. We have no Herget numbers, but we still have to include -1 and 1 because that's where we have these vertical asymptotes happening here. All right, so let's put in our test numbers. -2, we can use a 0, and we're going to use a 2. On the top is actually always going to be positive because 3x squared is positive. We're adding a positive to it. 10 is positive, so always positive on the top. We only are concerned about the bottom one here. Okay, so -2 squared is 4. 4 minus 1 is positive. This will be plus. If we put 0 in here, we have -1, but it's cubed. So -1 cubed is a negative number. So we do get a minus there. And then put 2 in here. 4 minus 1 is 3 cubed is positive. So now we have plus, minus, plus. What that's going to tell us is concave up on these ends and then concave down in the middle. All right, so concave up is where we're going to be plus, and so that's -infinity to -1. And then it's going to be from 1 to infinity. That's where it's concave up. It's concave down where it's negative, and that was between -1 and 1. So I'm just kind of writing down what we had from our number line graph at the bottom. That's the results that we get there. Now, inflection points. We might think that there's inflection points at -1 and 1. However, remember, these are undefined in the original function. So we can't have any inflection points because these points don't exist on the graph because we have vertical asymptotes here. So for inflection points, we actually have to put on this one D and E. Now we have everything that we need in order to graph this. So we put our 1 point that we found in there. That's the only one we have. And then we have to use our increasing, decreasing, and concavity to fill in the details here. We know that it is increasing from -infinity to -1. At the same time, -infinity, -1, it's concave up. So we have to draw a line that is both increasing and concave up. Now, if you remember from pre-calculus, a line is going to follow the dotted line here, and it's going to follow the other one there. So it's going to follow this one, and it's going to be increasing, and then it's going to go follow this one. That would be increasing, and that's also curving. Let me make that look a little bit better here. So kind of curving up like this. We don't want to have any flat part there. So there we go. So now it's increasing, and it's concave up. Okay, next thing is we got on this second number, this chart right here, we have -1 to 1 is negative. That means it's going to be concave down all the way between -1 and 1. Now it is going to go through this point right here. The graph does go through there. So here's what's going to happen. That it's going to go and it's going to end up looking like this. It's going to go here, curve, and it's going to go back down like that. So it has to be this kind of, it has to go through that point right there. So it matches our increasing, decreasing. It's supposed to be increasing between -1 and 0, and then decreasing from 0 to 1 is what we had before. And the last step is we have concave up over here on this side. So because it's concave up, it's going to have to follow this dotted line like that. It's going to curve and then follow this other one. And so that is what our final graph is going to look like by putting everything all together.